Hi guys, welcome back. So today we are going to continue with looking at the mole and doing our conversions using Avogadro's numbers. So just to review, we know that 1 mole of anything is equal to 6.022 times 10 to the 23rd. Okay? So if we have 1 mole of atoms, that's 6.022 times 10 to the 23rd atoms. Or if we have 1 mole of molecules, that's 6.022 times 10 to the 23rd molecules. Ever we refer to 1 mole, that's how many we have. We then took a look at to see what does a mole actually look like. And we saw that our atomic mass from the periodic table told us how many grams are in 1 mole of that substance. Okay? Or in other words, how many grams were in 6.022 times 10 to the 23rd particles of that substance. And this is going to be what we call molar mass. Okay, so molar mass is going to be that mass in the periodic table, and that is how much 1 mole of a substance weighs. And we saw our unit for this were grams per mole. Okay, and since we have that per there, we know we can use it as a conversion factor. And this is going to be what we look at today. So we said our molar mass, or the mass of 1 mole, we could find by looking at a periodic table. If we have a compound, we're going to do the same thing. We just need to add up our individual masses to find the molar mass of our compound. So if we have baking soda here, NaHCO3, we would find our mass of sodium plus our mass of hydrogen from the periodic table plus carbon, and then we have 3 oxygens. So we need to do 3 times that atomic mass of oxygen equal the molar mass of our entire compound. Okay. All right, so let's go ahead and get some practice using this information. All right, so in our first one, we want to see how many grams there are in 3.2 moles of calcium hydroxide, of CaOH2. Okay. So we need a conversion factor in order to go from moles to grams. And our tool to do that is going to be our molar mass, because that tells us how many grams we have per mole of substance. Okay, so remember, we never start with a conversion factor. So we are going to start with what we are given. So we start with our 3.2 moles of CaOH2. We need to multiply that by a conversion factor that will cancel out moles and leave us with grams. Okay. So again, our tool to do that is going to be molar mass. So in order to find our molar mass of calcium hydroxide, we're going to look at the periodic table and see what our atomic masses are for each one of those elements. So if we look at calcium, calcium is going to have a molar mass of 40 grams per mole. Plus, if we look here, we have 2 OHs. So that means in calcium hydroxide, I'm going to have 2 oxygen atoms and 2 hydrogen atoms. So when I find the atomic mass of each of those on the periodic table, I'm going to have to multiply each by 2. So when I look at the periodic table, I'm going to see that my molar mass of oxygen is 16, and my molar mass of hydrogen is going to be 1.01. So again, we're looking at that number beneath our elemental symbol that is typically a decimal. So then we'll do 40 plus 2 times 16 plus 2 times 1.01. And we'll find that our molar mass here is 74.02 grams per mole. So what that tells us is that 1 mole of this substance has a mass of 74.02 grams. Okay. We can use this molar mass then as a conversion factor. So our first goal is to cancel out moles. If we have moles on top of this fraction, we're going to want moles on bottom of our conversion factor, which means we're going to put grams on top. So I look at my molar mass, and I'm going to see that I have 74.02 grams for every 1 mole. Number 1 is always going to go with mole. We're always talking about in regards to 1 mole. So then in my calculator, we multiply by everything on top. So do 3.2 times 74.02. And we find 3.2 moles of calcium hydroxide has a mass of 236.86 grams. His moles on top, moles on bottom canceled out, leaving us with grams. Example. In this example, we're starting with 95.2 grams MgNO32. And we want to see how many moles do we have in that mass. So we're going grams to moles. So again, our bridge in order to go between grams and moles is going to be our molar mass. Because that tells us how many grams we have in 1 mole, or grams per mole. So again, we never start with the conversion factor, so we're going to start with what we're given. We start with our 95.2 grams. We need to cancel out grams and convert that to moles. So we need to find our molar mass of MgNO32. So in order to do that, we're going to add up the individual atomic masses of each element. So if I look on the periodic table, magnesium is going to have a molar mass of 24.31. I have 2 nitrogens because remember, I have 2 NO3s. So I'd have to take my molar mass of nitrogen times 2. Nitrogen is going to have a molar mass of 14.01. And then I need to take 6 times my mass of oxygen because I have NO3 2 times. So that means I have a total of 6 oxygens. So I'll take 6 times 16, or that molar mass of just 1 oxygen. And when I put that in my calculator, I'm going to find that my molar mass of the substance is 148.33 grams for every 1 mole. Okay, so I need to arrange this conversion factor, or this molar mass, in a way that helps me cancel out my grams. So if I have grams on top here, that means I'm going to want grams on bottom of my conversion factor. Okay, so in this case, I'm going to say I have 1 mole for every 148.33 grams. Here I have grams on top, grams on bottom. They cancel out, and we're left with moles. Here, since that 148.33 is on the bottom, we're going to divide by that molar mass. And when we do that, we should find we only have 0.642 moles. Okay. And this makes sense because 95.2 grams is less than the mass of 1 mole, that 148. So we should get less than 1 mole here. Example is going to take it 1 step further. So now we want to see how many molecules we have in 95.2 grams of MgNO32. So in our previous example, we found out how many moles there were. Now we want to figure out how many molecules we are. So we saw in our previous example that we can go grams to moles by using our molar mass. Okay, that's the relationship we have between mass and the number of moles. We then are going to want to take it 1 step further. We're going to want to go from moles to molecules, or particles. So here we need to keep in mind that 1 mole is equal to 6.022 times 10 to the 23rd particles. So once I know how many moles I have, I'm then able to use Avogadro's number to figure out how many particles I have in that substance. So let's take a look and see what this would actually look like. So again, remember, always start with what you're given. We never want to start with the conversion factor. So start off with our 95.2 grams MgNO32. Okay. We want grams to cancel out though. That's always our first step. Cancel out the unit that we have. So our tool to cancel out grams is going to be our molar mass. So how many grams do we have per mole? So if we look up at our previous example, we already found the molar mass of MgNO32 to be that 148.33. So I'm dividing by 148.33 grams in every 1 mole. Grams on top, grams on bottom cancel out, and we're left with moles. This is exactly what we did in the previous problem. We then are going to be able to take it one step further, because we saw in our video yesterday, if I have 1 mole, that's the same thing as 6.022 times 10 to the 23rd particles, or in this case, molecules. So I have moles on top, moles on bottom cancel out, and I'm left with molecules. So again, we multiply by everything on top. So we do 95.2 times 6.022 times 10 to the 23rd, divided by 148.33. And we should find in the sample that we have 3.85 times 10 to the 23rd molecule. Okay. So in 95 grams of magnesium, you have 3.85 times 10 to the 23rd molecules. That is a lot of molecules. And again, this is why the mole is so helpful, is because our molecules are so tiny. It's easier to work with when we have the unit of a mole. Okay. Awesome. So in our next example, we're going the other way. So here we're starting with molecules, and our goal is to get to grams. Unfortunately, like we saw in our previous problem, we don't have a conversion to go straight from molecules to grams. However, though, we do have a conversion to go from molecules to moles, and that's going to be Avogadro's number. Okay. And then to go from moles to grams, we've seen that we can use our molar mass. Okay. So whenever you're going between grams and molecules, mole is always going to be your pit stop. Always convert to moles first. So go ahead and pause the video and try to do this one by yourself. And then when you're ready, come on back. So for this one, we should have gotten a final answer of 31.49 grams of LiNO2. So if you got this one, give yourself a little pat on the back. Awesome job. Woo! If you did not get this, let's walk through where this answer came from. So our first step, since we are given molecules, is to go to moles. Because we know that in 1 mole, we have 6.022 times 10 to the 23rd molecules. So if I have moles on top, moles on bottom, we're able to cancel, or sorry, molecules on top and molecules on bottom, we're able to cancel that out, and we're left with moles. So that would tell us how many moles of LiNO2 we have. We want to figure out how many grams we have, or what mass the sample has. So my tool to do that is going to be my molar mass, because I know for every 1 mole of LiNO2, we have a mass of 52.951 grams. We got that number by adding up the atomic masses from our periodic table. And remember, there's 2 oxygens, so you need to multiply that molar mass by 2. But so, I end up with moles on top, moles on bottom, they cancel out, and I'm left with grams, which is the unit that I want. And we can see that we have 31.49 grams of LiNO2. Okay. We are going to look at one more that is very similar to this one, because it'll bring up a good talking point. So if you didn't get that last one, try it again, pause the video, and come back when you are ready. Our end goal is to see how many grams are there in 3.58 times 10 to the 23rd atoms of uranium. We should have gotten a final answer of 141.51 grams. So if you got that one again, yay, congratulations. But let's walk through how we got this. So here we have atoms, and our end goal is to get to grams. But again, we don't have any conversion factor that go right from atoms to grams. But we do know that there's 6.022 times 10 to the 23rd atoms in 1 mole. So our first step is to convert atoms to moles. Because I have atoms on top, atoms on bottom, they cancel out, and I'm left with how many moles I have in the sample. Okay, so this is what we did yesterday. Our next step then is to go from moles to grams. And remember, our tool to do that is going to be our molar mass from the periodic table. So we need to find uranium on the periodic table. And uranium, that is the chemical symbol of U. So when you find uranium on the periodic table, we see that it's going to have a molar mass of 238.03. Since we don't have anything else bonded to that uranium, we can just use that 238.03. We don't have to add anything to it. But then we can see that we have moles on top, moles on bottom. So we're left with grams as our final answer. So when you guys do these, always stop at moles first before making the full jump to grams or to atoms. Okay. The reason why this is a good talking point is if we look between these two examples, our previous example, we had 3.58 times 10 to the 23rd molecules. And this example, we had 3.58 times 10 to the 23rd particles. Notice, though, how the mass for our sample of uranium was much bigger than our mass for a sample of LiNO2. So why, even though we have the same number of molecules or same number of particles, why do we have different masses? And the answer there lies in the weight of our atom. Okay, so if we compare 1 mole of lithium, it had a molar mass of 52.951. So 1 mole of our LiNO2 equaled 52.951 grams. However, 1 mole of our uranium had a mass of 238.03 grams. So we can see that our uranium is much more massive, so the particles are going to be bigger. So since we have the same number of molecules in a mole, we have 6.022 times 10 to the 23rd, and our mass of uranium for those 6.022 times 10 to the 23rd particles is larger. That tells us an individual uranium particle is going to be bigger, okay? So even though we have the same number of atoms, we end up with a different mass because each of those substances have a different molar mass on the periodic table. Those particles are different sizes. Okay. I hope this helps. Please let me know if you guys have any questions.